Okay, so I think we're in business as far as that is concerned. All right, so excuse me. So I know we didn't finish chapter one. I'm trying to remember. Can somebody tell me, did we do this part right here? Conversion factors and using conversion factors to do conversions from one unit to another. So can someone tell me if we have actually done that?
Yes, I think we did.
Okay, so let me scroll down. So we did these examples.
Yes.
Okay, good. We did this one. This be my example.
No, I don't know if we did that one.
Okay, all right. I'll take your word for it. So I'm just going to commence from this particular example right here. Okay, so let me do a full screen. Where is that? Okay, so this example deals with the concept of BMI. And if you're involved in the health sciences or, related fields, nutrition, whatever, then you would be exposed to this concept, this basic measure of what is considered to be a healthy size for a person, for an average person. It's called the BMI, which stands for Body Mass Index. It's based on the combination of a person's mass and height. And basically what you do is divide the mass expressed in kilograms by the square of the height of the person in meters. And the units, therefore, for BMI would be kilograms per meter squared. And the general rule of thumb when it comes to the application of BMI is that if the BMI exceeds 25, then the person is considered to be overweight. So the question is asking, what is the BMI of a person who is 69.0 inches tall and weighs 158 pounds? Give me 1 minute. I need to get, hold on 1 minute. I just realized I should have had something here with me to help me solve this problem. I'll be right back. Okay, folks, I'm back. Sorry about that. Okay, so basically, to solve this particular problem, the first thing I would do is, let me get to my writing function here. To solve this particular problem, what I would do is I would take the mass of the person, 158 pounds, and divide it by the height of the person, which is 69.0 inches, and I would square that, all right? Now, directly speaking, the resulting units would be pounds per inch squared, but we want to get the answer in kilograms per meter squared. So basically what we need to do is convert this into a value equivalent to, well, expressed in kilograms per meter squared, all right? So the question is, how do we achieve that? Well, what we can do is somehow find a way of converting from pounds to kilograms and from inches squared to meters squared. So basically we have to multiply whatever this is by conversion factors, and we're going to need at least 2, so that we can successfully convert the value expressed in pounds per inch squared to kilograms per meter squared. So let me rewrite this here, 158 pounds over 69.0 inches squared, all right? So the first thing, well, let me take out, the equal sign here, go back to my pen. Okay, so what we need to do, and it doesn't matter which one we do first. So what I'm gonna do is focus on converting from pounds to kilograms. So let me go to my chart here. So let me see if I can find this particular. So the chart you're going to use is the one that is provided in Canvas. If you remember, when you go to Canvas, if you go to Files, and then you go to, I think it's called Tables, you'll see, see if I can find it here. If you go to Tables, Chemistry, and what you'll find, of course, is the document several pages long, which contains, among other things, the conversion factors that you'll be using. So that's what I'm trying to find here. My other computer here is taking its time loading up. Come on. Okay, let me see if this would work. Okay, now he decides to do this. Okay, so according to the chart, 1 kilogram is equal to 2.2046 pounds. So the way I would represent that here is that I'm gonna put 1 kilogram here, and down here as a denominator, I'm gonna put 2.2046 pounds. All right? And the result of that is that this pound unit will cancel out with this pound unit. So the next step, so what we have done so far is successfully convert from pounds to kilograms, all right? Excuse me. So the next step is to convert from inches squared to meter squared. So that means that I need to find a relationship between the inch unit and the meter unit. Now, based on the same chart, they give us a direct relationship between the inch unit and the centimeter unit, right? And it is 1 inch is equal to 2.54 centimeters. All right? So that's a relationship between the inch unit and the centimeter unit. However, you need to remember that there is this raised to the power 2 inches squared, which means that we have to square this conversion factor right here. All right, so that the inch squared unit will cancel out with the inch squared unit, and you'll be left with centimeter squared down here. Then we can go from centimeter to meter squared, centimeter squared to meter squared, because as you should know, or as you can easily figure out from the chart, the relationship between the centimeter unit and the meter unit is 100 centimeter is equal to 1 meter. So therefore, in this case here, it's 100 centimeter, which would be placed as a numerator, and 1 meter would be the denominator. And again, because you have centimeter squared from the previous conversion factor, that means you have to square this conversion factor right here, so that this centimeter squared unit will cancel out this centimeter squared unit, and you'll be left with the meter squared unit. So basically, after doing all this calculation here, your final answer would be in the required unit, which would be kilograms per meter squared. So all you have to do now is get your calculator and do your number crunching. So let me do that here with my cheap calculator. 158 divided by 69.0, and that is squared. Divided by 2.2046, and then divided by 2.54 squared, and then multiplied by 100 squared. And the answer I got is 23.3. So let me write that here. 23.3 kilograms per meter squared. Okay, and of course you have to make sure that you round off your answer to the lowest number of sig figs, which in this case would be 3 sig figs because you have 3 sig figs here. You have 3 sig figs here. This here, the number of sig figs here is 4. This is an exact relationship, so this has an infinite number of sig figs. And this is also exact, so also has an infinite number of sig figs. So this would be the final answer. And according to the what do you call it now? The scale, the BMI scale, and what is determined to be representative of somebody who's overweight. This person, whoever this person is not considered overweight because it falls below 25. All right. Okay. So that's basically how this is done. Any questions? Anybody has any question about this particular example? I haven't been checking. Oh, there's nobody in the chat. But any questions, feel free to ask questions. And feel free to stop me at any time if there's something that's not clear to you. All right. But are there any questions? Any questions? Okay, so let's move along to density, which is another measurement. It's actually a combination of 2 measurements, and it's a very useful concept because it is used as one of those identifying characteristics of a substance. It's a physical property. It's specifically a quantitative physical property, and it is by definition the ratio of the mass to the volume of a substance, and can be represented by this formula right here. D is the density is equal to mass over volume. So as such, the unit of density is dependent on the units that you use for mass and volume. All right. Now, for solids and liquids, let me just write this here. For solids and liquids, typically, we use liquids. We use the mass units in grams and the volume units in centimeters cubed, all right? So therefore, the density would be expressed in grams per centimeters cubed, all right? However, for gases, instead of using centimeters cubed, we use liters for the volume, which means that the density in this case is expressed normally in grams per liter. So this is the units typically for density if you're dealing with gases, all right? And the main reason why that is so is because when you compare gases to solids and liquids, for the same mass, gases tend to occupy a larger volume. So therefore, as a result, because it occupies a larger volume, it is more convenient to use a larger volume unit when it comes to determining the densities of gases, all right? Now, as stated here in this line right here, density can be used as a conversion factor. So for example, methanol has a density of 0.791 grams per mil. So therefore, we can represent this value as 2 conversion factors. Either this one, where the mass is the numerator and the volume is the denominator, or the other way around, where the volume is the numerator and the mass is the denominator. And which one you use is dependent on what problem that you're trying to solve. You would use this one if you're given a volume and you're trying to find a mass of the substance. You would use this one if you're given a mass and you're trying to find what did I say before? You use this one if you're given a volume and you're trying to find the mass of the substance. You would use this one if you're given a mass and you're trying to find the volume of the, no, I think I just repeated myself. This you'd use if you're given a volume and you're trying to find a mass. This is what you're going to use if you're given a mass and trying to find a volume. All right. So let's look at a couple of examples right here. So this one, the first one, talks about what liquid? The same methanol, right? And in fact, using this information here, we're actually going to confirm the density that we just stated. So let me just do a little something here on this side right here. Okay, let's do this. Okay, so I'm going to get out of this. Okay, let me read this question first, and then I'm going to solve it separately. So this question says, a beaker has a mass of 85.2 grams when empty and 342.4 grams when it contains 325 mils of liquid methanol. So the question is asking, what is the density of the methanol? All right. So what I'm going to do is get out of this, and I'm going to pull up one of my writing applications here. Let me use this one. Let me see if this one would work. Sometimes these act up right in the middle of my teaching. Okay, so let me see if my pen is working for this. Okay. It seems to be too broad a tip. Anyway, let me see if I can work with this. Okay, so let me reread the question again. The question says, the beaker has a mass of 85.2 grams. So mass of beaker is equal to 85.2 grams. And then the mass of beaker and liquid is equal to 342.4 grams. So therefore, the mass of the liquid is equal to 342.4 grams minus 85.2 grams. So where's my calculator? So let me do this here. 342.4 minus 85.2 equals, so the answer here is 257.2. 257.2 grams, all right? So the question is asking for the density. So the density based on this would be equal to the mass over the volume. The mass is 257.2 grams divided by the volume. And according to the question, the volume is 325 mils. So let me do that calculation. So I divide the 257.2 by 352 mils. And the answer I got here, and again, you have to round off to the lowest number of sig figs, which in this case would be 3. So therefore, this would be 0.731, and the units would be grams per mil. And that's basically how the first example is done, all right? Anybody have any questions about this particular example? Any questions? Okay, so let me minimize this and move on to the second question, which says, how many kilograms of methanol does it take to fill the 15.5 gallon fuel tank of an automobile modified to run on methanol? All right, so basically in this case, they gave you the volume, right? And the question is asking for the mass of methanol. So you have to use the information that you got from the first part, all right? Because the first part gives you the density. If they gave you the volume and they're asking for the mass, that means that you're going to need the density of the liquid. Now, what I'm going to do is try a different writing application here. Let's see if this one gives a better, oh yes, this is nice. All right, so let me erase this here. And hold on, wait a minute. Let me scroll down. Okay. And how shall I make this larger? Oh, zoom right here. Okay, this should work. Let's see here. Okay. All right, it's not working. What is going on? Okay, I thought this would be working for me, but apparently it's not. Okay, I don't know what's going on with that. So let me get out of that. And let me go back to this. And let's just work with this one. So what I'm going to do is get rid of that. Okay, so the next part is they gave you, as I said before, 15.5 gallons, and you're to find out the volume, I'm sorry, not the volume, but the mass in kilograms of the methanol. So what I would do is start off with the 15.5 gallon. In fact, let me do this. What I would do is convert the gallons to centimeters cube. So I would have to go to my table to see how I can do that. So let me see here. Let me go here. Okay, so according to the table here, let me see what I can find here. According to the table, I can go from gallons to quarts, and then there's a relationship between quarts and liters, and then there's a relationship between liters and centimeters cube, and then using the density, I can go to grams, and then I can convert to kilograms. So this is one way of doing it, and I'm quite sure there are other ways of going from gallons to kilograms, which is probably shorter. Let me see if I can find a short alternative. Well, I can't find one based on what I have here, so I'm just going to go work with this here, right here. Okay, so I'll start off with 15.5 gallons. And according to this, hold on, wait a minute. Actually, I don't need to go to quarts. I can go from gallons straight to liters, all right? So to go from gallons to liters, according to the table, 1 gallon is equal to 3.7854 liters, all right? And then to go from liters to centimeters cube, the relationship is 1 liter is equal to 1,000 centimeters cube. And then based on the calculation we did before, we found out that the density is 0.731 grams per liter, or per centimeters cube, I'm sorry. So I'm going to put 0.731 grams up here, 1 centimeters cube down here. And then finally, I will convert from grams to kilograms. And that means I'll put 1 kilogram here as the numerator, 1,000 grams down here as the denominator. So the units that will cancel out would be the gallon units, the liters units, the centimeters cube units, and the gram units. And the only unit remaining would be the kilogram unit, all right? So what I'm going to do is just put the numbers in my calculator, 15.5 times 3.7854 times 1,000 times 0.731, and then divide by 1,000. And according to my calculations, again, we have to round off to 3 sig figs. When I do that, the answer I got is 42.9 kilograms. And that's the answer. All right? Okay, any questions about this particular example? Any questions? Any questions? Okay, so I think that's basically it for this chapter. Let me just check something here. Okay, so that's it for this chapter. So what I'm going to do now is start chapter 2. Oh, before I move on to that, let me just remind you that there's assignment 1 or assignment chapter 1, which is still available. And in fact, I made copies for you guys and I gave it to you guys in class, all right? So you should still have it. So based on what we have completed, now you should be able to complete that assignment, all right? Now, before I got ill, I was hoping that I would receive that assignment today, but of course, I was ill, so things have to change in terms of scheduling of assignments and so on. So for this assignment, it's going to be due next week. Hold on 1 minute. It's going to be due next week, Tuesday. All right. So make sure you complete it. And when you do these assignments, I want you guys to take the same approach as I did, just as I showed you just now. Make sure that you show, the working. Make sure that you show the setup. Make sure that you show all the units. And also, very important, make sure that you round off your answer to the correct number of significant figures. All right, very important. Okay, so with that said, let me get out of this chapter. And let's move on now to chapter 2, which deals with, again, several topics that you would have encountered in your introductory chemistry courses. So again, this will be a bit of a review. Atoms, molecules, and ions. And first thing I'm going to talk about here are several laws which concerns reactions, laws of chemical combinations, right? And the first law that we're going to talk about is what is known as the law of conservation of mass. And basically and if you look in different textbooks, you'll see that this law is worded in different ways. So the way it's worded here is probably the simplest. Excuse me. The total mass remains constant during a chemical reaction. In other textbooks, you'll see that it's worded in a chemical reaction, matter is not created nor destroyed, right? But converted from one form to another. So there's several ways of expressing the same law. But basically what this law is saying is that if you have a reaction and you take the total mass of the reactants, and then at the end of the reaction, you take the total mass of the products, the total mass of the reactants and products will be the same, all right? So that's the first law of chemical combination. Now, the next law we're going to talk about here is called the law of definite proportions. And basically what this law says is that if you take a particular compound and you break it down into its constituent elements, then the proportions of the different elements by mass will be the same. And it doesn't matter where you get the compound is. If it's the same compound, then its composition is going to be the same. So as you can see here, this is one way of wording this law. It says all samples of a compound have the same composition, or all samples of the same proportions have the same proportions by mass of the elements present, all right? So that's called a law of definite proportions. So an example of this law is shown here. Now this compound, to be perfectly honest, I don't know what the compound is, but in any case, they gave you the composition right here. This particular substance contains 57.48% copper, 5.43% carbon, 0.91% hydrogen, and 36.18% oxygen. And it doesn't matter where you get this compound from, as shown here, it's the same composition. A simple example would be water. I think we talked about the composition of water before, but just in case I haven't, water has a composition of 89% oxygen and the rest 11% hydrogen. And it doesn't matter where the water comes from. If the water comes from the rain falling from the sky, or if you get the water from a river or from your tap, it doesn't matter where it comes from, the composition is still the same, right? So that's basically what the law of definite proportion says. It says that for a pure substance, the composition of that substance by mass would be the same, regardless of where you get that substance from. Okay, now why is this thing not responding? Okay, oh, this is basic copper carbonate. Okay, so so the point being made here is that basic copper carbonate comes from these three different sources, but it's the same composition. All right. Okay. Now that brings us to this example. So this question is dealing with a compound known as magnesium oxide, and it tells you that the mass ratio of oxygen to magnesium is this right here, 0.6583 to 1, right? So basically for every 1 gram of magnesium, you have 0.6583 grams of oxygen. So the question is asking, what mass of magnesium oxide will form when 2.00 grams of magnesium is completely converted to magnesium oxide by burning in pure oxygen? So the way I would tackle this problem is, let me go to my pen right here. Okay, so what I would do first is start off with the 2.0 grams of magnesium, and I will multiply that by the ratio of magnesium to oxygen, or more accurately, oxygen to magnesium. So I'll put 0.6583 grams of oxygen for every 1 gram of magnesium. So that goes with that. So let me do the calculation here. So that's going to be 2.00 times 0.6583. And the answer I got is, okay, I have to round this off to 4 sig fig. So this is going to be 1.317. 1.317 grams of oxygen. Now we're not finished because the question is asking for the mass of magnesium oxide that will form. So far, we have determined the mass of oxygen that will react with this mass of magnesium, which is 2.00 grams. So therefore, the answer is that the mass of MgO formed would be equal to 2.000 grams plus 1.317 grams. So plus 2. So the answer I got is 3.317 grams. And that would be the final answer. All right, so that's basically how that is done. All right, any questions about this example? Any questions? Any questions? Okay, so let's move along. All right, so another law, and this is probably the last thing I'm going to discuss today. So the other law deals with law of multiple proportions. And this is a bit wordy. I'm going to try to explain it as best as I can. Whoops, sorry about that. So let me just read through it first. So it says, when two or more elements of different compounds of the same two elements are compared, the masses of one element that combine with the fixed mass of the second element are in the ratio of small whole numbers, all right? So let me try to explain what all of this is saying by using the example that will be on the next slide. So here we have two compounds, carbon monoxide and carbon dioxide, right? They're both made up of the same elements, all right? Now, if you compare these two, let's say you have a certain amount of carbon monoxide in which it contains 3 grams of carbon, and you have a certain amount of carbon dioxide which contains the same mass of carbon, which is 3.0 grams, right? If you were to compare the mass of the other element in both cases, which would be oxygen, what you'll find is that the ratio of those two elements, or of the same element, the other element, would be a whole number ratio if the amount or mass of the first element is fixed. So in the case of carbon monoxide compared to carbon dioxide, the mass of carbon is the same in these two examples, but you'll notice that the mass of oxygen is of a ratio, in this case, 2:1, right? And that's basically what this law of multiple proportion is saying. It's saying that if you have two compounds, and in fact, two or more compounds, where the mass of one element is the same, and the mass of the other element is not the same, not necessarily the same, then the mass of the other elements would be in whole number ratio when you compare those two compounds. And that is seen in this particular example of comparing carbon monoxide to carbon dioxide, right? The mass of carbon is the same in both cases, but the ratio of oxygen and carbon dioxide is to the mass of oxygen and carbon monoxide is a 2:1 ratio, which they go through all this here, but basically the ultimate result is that the ratio of oxygens in both compounds is 2:1, right? And that is seen in other examples. And of course, one could have predicted that based on the formulas. You notice that there's a 2 here as a subscript compared to the 1 here in the case of carbon monoxide, all right? And that is seen in other compounds. For example, if you were to compare, let me get out of this here. If you were to compare, actually, let me use this example that I have right here. So let me go through all this here. If you were to compare these 4 compounds, right? N2O, N2O3, N2O4, N2O5, right? And if you have 28 grams of nitrogen in each of these cases, and if you look at the masses of oxygen in each case, what you'll find is that there's a simple whole number ratio when you compare those masses. So in the case of 28 grams of nitrogen in each of these compounds, for compound 1, the mass of oxygen is 16. For compound 2, the mass of oxygen is 48 grams. For compound 3, it is 64 grams. And finally, in compound 4, it is 80 grams. What you'll see is that it's going to be a small whole number ratio, which would mirror the numbers that would be the subscripts for oxygens in each of these cases. So in other words, the whole number ratio here between these 4 compounds would be 5 to 4 to 3. Whoops, I'm sorry. 5 to 4 to 3 to 1, all right? So that's basically what this law is saying. That's called the law of multiple proportions. All right, okay, I'm going to stop here. So the next time we meet, we're going to be discussing Dalton's atomic theory, and then we're going to discuss the formation of ions and molecular compounds. And I think the rest of this chapter will deal with naming these compounds, all right? The rules for naming, nomenclature. Okay, so that's basically it for today. So let me apologize if I sound weird, because while I was teaching, while I was conducting this lecture, I started feeling congestion. So I'm quite sure it's reflected in my voice, all right? Are there any final questions or any issues, problems you guys have?
For clarification, the
Uh-huh.
worksheet number 1 is that,
Uh-huh.
did you say that's due next Tuesday?
Yeah,
Okay.
right.
So I'll just turn it in class then.
Yeah, you can turn it in class, yeah.
Okay.
Yeah. Any other questions? Any other questions? Okay, so if there are no other questions, that's it for today. So I'll see you guys on Tuesday, and I'm hoping that I sound much better than I am right now. All right, so take care. And by the way, I'll be available for office hours also online tomorrow. If you look at the syllabus, you'll see that I'll be available. Let me see. I'll be available from 10 to 12 and then from 2 to 5. All right. So if you have any questions concerning, the assignments, you can contact me during that time via Skype. All right. Okay. So that's basically it. So as I said before, I'll see you guys next Tuesday. So until then, take care.
See you next week.
You too.